Hi, in this video, we'll be telling you about the microlearning project developed for NeuroMatch's NeuroAI course. Specifically, we'll be delving into the topic of credit assignment and local learning rules in artificial and neural systems. This project was developed by me, Colleen Gillon. I'm a postdoc at Imperial College London, and my colleague, Klara Kaleb, is a PhD student at Imperial. In the video, we will be touching on topics that are core to biologically plausible learning, but you'll be delving into these in more detail on the microlearning day of the NeuroAI course. The fundamental question that we're asking in the field of microlearning is, how do neurons learn? Specifically, how do individual neurons know how to adjust their synaptic weights during learning to optimize a network's overall performance? As you can imagine, with a small network that just has a handful of neurons and synaptic connections, this coordination task could be fairly straightforward. But as networks become larger to serve more complex tasks, this coordination task is actually quite complex. We call the problem of how to coordinate synaptic weight updates across a network the credit assignment problem. Now, when it comes to solving the credit assignment problem, it is evident when you think about it that the brain has a pretty good solution. We know this because humans and other animals are quite good at learning a large variety of tasks. So clearly the brain is doing something right, but the question is, what is it doing? We might look to deep learning to give us some ideas, where the leading solution is gradient descent via error backpropagation, which you'll have learned about in a deep learning course. So this raises the question, does the brain use this solution? Does the brain use backpropagation? Well, in support of this idea is the fact that backpropagation is by far the most successful, most scalable algorithm that we know of for learning in deep neural networks. But on the other hand, as you may have anticipated, backpropagation raises some significant biological plausibility problems. One of the major problems, though not the only one, is the weight transport problem. This problem is also called the weight symmetry problem, and it comes from the fact that when you're performing gradient descent via error backpropagation, the error that you've computed has to be propagated backwards through the network to each neuron via symmetrical feedback weights. So what does this mean for the brain? Well, if the brain is doing backpropagation, it would have to have feedback connections that are symmetric to its feed-forward connections, through which it sends gradients backwards. And embedded in this is another biological plausibility problem. Let's not forget that in deep learning, the feedback connections through which you pass the gradients do not affect network activity. So you need to have not only exactly symmetric feedback connections through the brain, but they would have to somehow not affect feed-forward network activity. There's really no evidence in neuroscience that the brain has these kinds of connections to rely on in order to do something like backpropagation. So whatever the brain is doing, it most likely isn't backpropagation, at least not as we see it implemented in deep learning. So how does the brain solve the credit assignment problem? Many alternatives have been proposed to backpropagation to address its various implausibilities. We should keep in mind, though, that no algorithm proposed to date is perfectly biologically plausible, addressing all possible plausibility limitations. But several alternative algorithms have been proposed that avoid some of the major implausibilities of backpropagation. You're going to be looking at these in more detail on the microlearning day of the NeuroAI course, so here we just give you an overview of a few categories. The first category are local learning algorithms. For them, the idea is that two neurons, in order to update the synaptic weight between them, do not rely on any external information, so not even a global error signal. An example of this is Hebbian learning, which was made famous with the expression, neurons that fire together wire together. And so here, the update between two neurons depends on whether they fired approximately at the same time. Now, another learning algorithm in this category is spike timing dependent plasticity. This is an algorithm used in spiking neural networks. And here, the idea is that if you know the relative timing of spikes in a pre- and postsynaptic neuron, that will directly determine how you update the synaptic connection between them. Now, another category of algorithms do rely on an error signal, but it's a global error signal, so you don't need to feed back gradients to each neuron. These include perturbation-based algorithms. In these algorithms, what you do is you compute a global error signal, And then you perturb the activity of the neurons, or you perturb the weights between them, and you observe whether the error signal has improved. And if it has, then you apply the weight updates that underlie the perturbation that you've tested. A third class of biologically plausible algorithms are algorithms that aim to approximate backpropagation, but do not force you to rely on exactly symmetric feedback connections. And these include feedback alignment and the Colleen-Pollack algorithm, both of which you'll be looking at on the Microlearning Day of the NeuroAI course. Now, there are a lot of other algorithms in this category. Some of them are variations on the ones that we just introduced, and some of them are really altogether new ideas for how to do biologically plausible learning. For a really helpful overview of the topics we just covered, you should take a look at Lillicrap and colleagues' 2020 Nature Reviews Neuroscience paper. Now, what is the downside of learning with these algorithms? Well, the major downside is that more plausible algorithms tend to scale less well, to deeper networks, to harder tasks, to online learning. They don't generalize as well, which is a major limitation if you're trying to train a deep neural network that behaves like the brain. But that's something that we should keep in mind. The brain itself is a pretty good and also pretty energy efficient learner. So whatever algorithm it's using, which by definition is biologically plausible, it must be pretty good. Now, this brings us to two major questions in microlearning in NeuroAI. One, can we devise biologically plausible algorithms that learn well? And two, can we figure out which learning rule or learning rules the brain is using? Now, to achieve these two goals, one thing that we need to be able to do is evaluate a learning algorithm. Now, some of the more straightforward ways of doing this are to measure the quality and rate of learning that an algorithm enables, right? So this is pretty standard, measuring accuracy in classification or reconstruction fidelity, measuring the number of epochs it takes for an algorithm to converge to the best solution. Another thing, of course, that you'll measure is generalization. So the most obvious instance of doing this is that you typically want to evaluate your network on a held-out test set. But you might also want to evaluate it on an out-of-distribution held-out test set to see how well it's able to generalize to new conditions. Another way to evaluate learning algorithms is to see if they're robust to noise in the input, to switching tasks partway through learning, or to online learning, where you're learning with a batch size of 1. We can also take a look more closely at how an algorithm is learning. So when we think about it, a really good way to learn, as we know, is to follow the gradient of the error. So what we can do is we can take the weight updates that an algorithm of interest proposes and compare them to our quote-unquote ideal updates that you would get if you followed the error gradients. Then you can take a look at the overall variance and the overall bias of your algorithm's weight updates when compared to these ideal updates. To illustrate this, we have a figure here taken from Marshall and colleagues' 2020 Journal of Machine Learning research paper. Now, in both panels, in blue, you'll see updates that follow a quote-unquote ideal update pattern, following the error gradient. In panel A, you see in green the updates proposed by a different learning algorithm. And as you can tell, the errors do end up bringing you towards the same minimum in the loss landscape. However, they're darting back and forth across the blue line. So these are updates that have very high variance, even though they have a low bias because they bring you to the same point. In the B panel, what we'll look at are the brown arrows. And as you can see, these have a low variance, so they're not really darting back and forth across the loss landscape, but they do bring you to a different point compared to the blue arrows. So we would say that this is an algorithm that has low variance, but a higher bias. Now, what we can do is consider that when we're looking to identify a good biologically plausible learning rule, we probably want to look for a candidate algorithm that has low bias and low variance, basically that learns pretty well. In order to determine whether an algorithm has low bias and low variance, you'll want to have your ideal updates to compare to. So we could consider backpropagation as the best algorithm we know for learning along the gradient of the error and use its proposed updates as our ideal updates. We can then compare the updates proposed by different algorithms of interest to these ideal updates. What we typically find is some algorithms do have low variance in their updates, but they're highly biased. And others have fairly unbiased updates, but they have very high variance. And it tends to be difficult to find a biologically plausible algorithm that does well on both low bias and low variance. However, there have been some really excellent improvements in this field, but it really remains a field in which there are lots of potential. There's lots of potential for new discoveries and new work. Now, before we get to our projects that will be looking into these questions, we did want to raise one final question that is quite important. And that is the question of, does the brain even follow error gradients when it's learning? We know that the brain is a good learner, but it may not be a perfect learner. So what we want to do when we're trying to see what the brain is doing is not just assume that it's doing perfect learning. Instead, we want to collect the same metrics, quality of learning, speed of learning, things like the bias and variance that we've just discussed, in a set of candidate algorithms, but also in the brain, and then identify which algorithms behave most like the brain. Now, you may have been able to guess just from thinking about how you would go about this, that this is a fairly challenging task to accomplish. But it is the type of comparison that could produce some really helpful insights about what the brain is doing. So it's definitely worth looking into. And in fact, you can take a look at Nayebi and colleagues' 2020 NeurAPS paper, where they present their study on the reliability of using different network learning metrics to infer the learning rules that a network was trained on. This brings us to our project map. So in the first questions and steps of the project map, a lot of them do overlap with what you'll be doing on the microlearning day of the NeuroAI course, because the idea is to get you started in implementing and evaluating biologically plausible algorithms. So question 1, we propose that you implement a simple feed-forward network that does MNIST classification using backpropagation. In question 2, we then propose that you take out the backpropagation from your learning and instead implement a biologically plausible learning rule of your choice. Hebbian learning, weight and node perturbation, feedback alignment, the Colleen-Pollack rule, for example. Then in step 3, we invite you to choose a few overall learning metrics that you would like to measure in both algorithms and compare between the two. So these can be, as we discussed earlier, classification accuracy, an F1 score, the number of epochs it takes for your network to converge, really any metric that you would compute in order to assess the quality of learning in your network. Question 7 is a little bit more challenging, and it invites you to measure the bias and variance of the weight updates. So this is something that we've discussed in this video, but also that is covered on the microlearning day of the NeuroAI course. And then, having come up with ways to compute all these metrics, we propose in question 4 that you implement a second biologically plausible learning rule, compute the metrics for both, and compare them to see what are the advantages, the disadvantages of these algorithms. Does one of them perform better than the other? Why might that be? Now, once you've gotten your feet wet and gotten used to working with these biologically plausible algorithms and these metrics, that's when the project map splits into 2. On the first path, you're going towards the question of, can we devise biologically plausible algorithms that learn well? In the second path, you're going towards the question, can we figure out which learning rule the brain is using? So looking at the first path first, specifically what you're invited to do is test more complex learning scenarios and learning rules. In question 6, we propose that you implement the remaining biologically plausible learning rules, the ones that we've listed in question 2, and test these in more complex learning scenarios. So this could be online learning, where you learn with a batch size of 1. It could be learning from non-stationary data. So for example, early in learning, you might remove all the examples of 6s from your training data, and then only introduce them later in learning so that the distribution of your training data changes across learning. Another more complex scenario is learning with noisy inputs. So look for some complex scenarios that are of interest to you and see how the biologically plausible learning rules fare with these. In question 10, we propose that you look in the literature for a different biologically plausible learning rule, perhaps a more complex one that's of interest to you, and implement it. So this could be, for example, target propagation, predictive coding, spike time-dependent plasticity, or burst prop if you want to use a spiking neural network. So implement one of these algorithms, or maybe an enhanced version of the algorithms proposed in question 2, and then test these in your basic scenario and also potentially in the more complex scenarios. See which ones work better, which ones are more robust, which ones you really struggle to train successfully. And through following this path, we hope that you'll get an interesting view of the landscape of biologically plausible algorithms currently being used and being proposed. Now, if you go through path B, here, to address the question of whether we can figure out which learning rule the brain is using, we propose that you try to infer the learning rule a network was trained with. In question 5, we propose that you implement the additional biologically plausible learning rules from question 2, and then evaluate how consistent the metrics you've computed are for each rule. So for example, what happens if you take a network and train it 5 times with the same learning rule, but each time with a different random seed? Do you find that the metrics you've collected are fairly consistent across random seeds, such that from the metrics you could infer the learning rule that was used? In question 8, we invite you to take that a little bit further. So what happens now if you don't only change the random seed, but you also change some of the network's hyperparameters? So obvious examples of this could be adding units into your hidden layers, whether through width or depth of your network. When you've made these changes to the networks, are the metrics that you've collected still fairly consistent for the same learning rule? Can you identify from the metrics which learning rule was used to train your network, even though the hyperparameters are variable? The idea here is that if we're trying to understand what the brain is doing, we do need to have metrics that are fairly robust to changes that really don't have to do with learning rule, but just have to do with, for example, architecture. Now in question 10, here we ask you to think a little bit about the limitations technologically that we have when we are collecting data in the brain. So although technology has advanced really substantially, we still have some pretty major limitations. For example, you wouldn't be able at this point in time to measure the synaptic weights between all neurons at all time points across learning. At best, you probably would get a snapshot at a few points across learning. And what's even more likely is that you'd have to rely on network activity to infer the weight connections between the different neurons. Another limitation that we have is we can't typically measure information from all the neurons in the network, right? In the brain, we're really just capturing a subset. So what we propose is that you select a few of these limitations and apply them to your metrics. What happens if I compute my metrics, but only at every 5 epochs? What happens if I compute my metrics, but only using a third of the network? Am I still able to use these metrics to infer the learning rule that the network was trained on? So the idea in this path is really to understand what are good ways of trying to understand what a network is doing, and specifically what the brain is doing when it comes to the learning rules that's implementing. And that brings us to the end of this video. Thank you for your attention, and we hope you really enjoy working on whichever project you choose to work on.